DYNCAT, which is short for Dynamic Configuration Adjustment in the Terminal Manoeuvring Area, is a collaboration project with project partners from Germany, France, and Switzerland. The goal of this project is to factor environmental quantities like CO2 and noise when optimizing flight trajectories, enabling safer, more cost-efficient and more environmentally sustainable operations in the Terminal Manoeuvring Area. Within this project, we developed onboard system functionalities that help the pilots with the configuration and energy management during approach. This includes the optimized settings of flaps and landing gears, but also the thrust setting in order to reduce noise and fuel consumption. To demonstrate the capabilities of the DYNCAT functions to reduce noise and CO2 emissions, we conducted simulator flights with experienced pilots. These were approaches to runway 14 at Zurich Airport in Switzerland. In the following, we show a very specific situation, where the pilots were forced by the air traffic control to make a shortcut during descent and are situated in an over-energy state, meaning that the aircraft has excess potential and kinetic energy, which has to be dissipated during the approach, without generating unnecessary noise and burning more fuel. We have simulated two exemplary flights, one with the use of the DYNCAT functions in blue, and a reference flight in gray, without the support of DYNCAT. We calculated both flights with the aircraft noise calculation model SUNAIR and show the differences of the momentary sound pressure levels on the ground. We have stretched out the reference flight in time so that both flights are above each other and can be compared in a meaningful way. The visualization of the level differences is reduced to an area where the current sound pressure level of the flight with DYNCAT is greater than or equal to 40 decibels. Green-colored areas indicate that the flight with DYNCAT is quieter than the reference flight. Orange means that the reference flight is quieter. At this stage of the approach, we see that the reference flight has already reduced altitude and flies at a roughly 1,200 feet lower height, which indicates two different approach strategies. As the DYNCAT flight is significantly higher at this time, the noise impact on the ground is also lower. Here you can clearly see that a dark green wave front is spreading. This means that a configuration change was made on one of the two flights, which causes the level difference to become even greater, in favor of the DYNCAT flight. The DYNCAT flight is not only moving higher at this point, which reduces noise impact on ground, but, without increasing thrust, is also faster in order to reduce approach time and thus the fuel consumption. This is achieved through optimized energy management. On the DYNCAT flight, the altitude is now continuously reduced until the two flights are at the same altitude. Noise differences can now no longer be explained by different flight altitudes, but by different flight speeds, engine thrust and configuration settings. At this point, the DYNCAT flight produces more noise than the reference flight, mainly due to the increased airspeed. In this case, it does not mean that DYNCAT is not working or is set incorrectly for this flight segment, but that more attention is being paid to fuel savings, resulting in an increased flight speed. This reveals a trade-off between fuel consumption and noise reduction. Faster flying aircraft are generally noisier but consume less fuel due to the shorter flight time, at least with the engines operating at idle thrust. Depending on the requirements, DYNCAT can optimize one or the other. And as can be seen with this example, it is also possible to find a balanced optimum that results in a lower noise burden for the residents and lower CO2 emissions at the same time, compared to standard approaches without DYNCAT. We now see that for the reference flight, flap stage 2 is already extended, but at the same time, the thrust is increased. This is unfavorable from an energy as well as noise point of view and can be avoided by using DYNCAT. At this stage, the two aircraft produce the same amount of noise, although the DYNCAT flight is substantially faster. We see now that flap stage 2 is extended much later in the DYNCAT flight and the airspeed is decreasing. We are getting closer to the final approach stage. As the absolute sound levels also become higher, low-noise flying is increasingly important in this area. The DYNCAT flight is now moving more slowly, which has a positive effect on the noise impact. The trajectory now also indicates that the landing gears are extended about 1 nautical mile earlier for the reference flight. Measurements at this airspeed have shown that the Airbus A321 is about 1 decibel louder with the landing gear extended than when they are retracted. The two flights are now at the stabilization point, from where the DYNCAT function is no longer active. We thank you for watching and encourage you to visit the DYNCAT homepage for more information.